Hi, so welcome to the third module. Okay, so what we're going to start talking about is basically boundary layers. Okay, so I guess you have really heard about the boundary layers. Now, the word itself is not like completely unknown to you. So let us, if you know, then let us just kind of revisit and try and understand what that means. And every time we talk about a boundary layer, we kind of always, going back to a flat plate, flat plate, flat plate. Fine, flat plate. We'll also look at boundary layers, but boundary layers could form at various places, right? So you could have, say, so basically what we are starting out to do today is boundary layers, and why at all is this important? Why is this important to even study? Okay, so say you have a flat plate. Every time we draw a flat plate, we kind of draw it in this fashion. But what exactly we are talking about is that the plate it's actually a plate like this. This is a flat plate, and you have, say, fluid coming in, some of the fluid coming in over there. But every time, so you could actually say that this is the z-axis, this is the x-axis, and this is the y-axis. Okay, and then we draw things like this, right? So every time we say draw a boundary layer, you kind of draw boundary layers like that. Draw a nice stuff like that, and then you say, okay, so this is the velocity profile. So what basically you're looking at, so every time you draw something like that, you should remember that you are basically, looking at a particular section on this flat plate, right, on this flat plate along y. So what do I mean by that? So essentially what I mean is that I could have, several sections. I could have several sections along this y. So if I were to, say look at this point, okay, so this line, okay, this section, or it could be, say, this section or this section. So then at all these sections, one would like to know the behavior of the boundary layer. So how would that look like? How would the velocity profile look like? How would the velocity profile look like somewhere here? So essentially what we are saying, that as we progressively move along the y direction, there are various sections at which there is a boundary layer. So I guess when you look at the picture that you see in the books, so basically you are looking at say a 2D boundary layer, right? So where you kind of either you're not talking about at all, or you're basically saying that you see the same thing as you move along. You see this particular picture, this kind of a velocity profile will not change if you move along y. That's what you're assuming. You don't know that actually. Okay, and of course you go along x. Of course there is a change in the velocity profile. Okay. So this is again what you see, but then boundary layers could be, you could have flow through a pipe, right? So you have a flow through a pipe, right? So you have flow coming in and flow goes out. Okay, so you have boundary layers forming like that, and you have boundary layers forming like that. So this, along the walls, right? So you could have boundary layers there as well. There is flow past a cylinder. Okay, again, so if I were to draw a cylinder this way, right? If you draw a cylinder this way, so what the fluid basically comes in this way. So if I were to take again, if I were to take a section again, so I go along this and I take a section, right? So this section is basically I basically cut through the cylinder. Okay, so what I will basically see is just a circle, right, which is similar to here. And then when I see that, so I have, say, flow moving in like that, then it, and I'm just, this is a streamline, you know. So maybe I'm doing this right, okay. Similarly, I've drawn on half of it, right. So you could do that. So when the flow comes in there, you know, you will see boundary layers forming here as well. So boundary layers are everywhere, okay, boundary layers are everywhere. And of course, then of course you have the, you know, shape, which I deal with most, you know, because this is what I kind of research on. So this is your airfoil, you know, this is your airfoil, this is 2D, okay, this is 2D, and again, you could have, you know, so you could think of this like, you know, a flat plate. So this basically, the section here we have changed. This is different from the flat plate that we talked about here. So this is different in the sense the section is an airfoil shape. Okay. So here too, as the flow, you know, as the flow comes in, as you have flow, as flow moves in, like that, you know, this is a cambered airfoil, so it will cause lift even when the angle of attack is 0, right, because of the shape. So then, you know, flow moves in this way and so on and so forth. This is a particular streamline. So here also the flow which is closest to the body will stick to it. As you move away from it, it will flow past and so on and so forth. So you could draw velocity profiles in this fashion, you know, you could draw velocity profiles in this fashion, okay, in this way. So these are the velocity profiles you could draw, and again here too you could draw velocity profiles. Okay, so here too you could draw velocity profiles. See if I'm right. Okay, so here too. Okay, so basically, you know, these are boundary layers. Now again, so what exactly is the concept here? What is this thing that it sticks to it and so on and so forth? How does this problem, you know, crop up? Now, this was basically Prandtl's, you know, theory. Prandtl's theory that the effect, the reason we have the boundary layers is one of the effects of considering a fluid with viscosity, right? So viscosity is a key term here, which we kind of discussed a little bit in detail probably in the first 2 modules, okay? So the viscosity is basically causes a retardation on, you know, a fluid which is moving, right? So that is what which basically, you know, it pulls this the layer of the fluid which is closest to it, it pulls it, you know, in the reverse direction to what it is actually flowing, and this pull decreases as you go away from it, right, as you go away from the plate or from the surface on which it is moving. Okay, so viscosity, however, is a property of the fluid itself, right? Unlike friction, please remember that unlike friction, where the surface, you know, property, it's a surface property, and that depends on it, right? It depends on the weight, because friction is equal, frictional force is a coefficient of friction into the normal force, right? So here, however, the viscosity itself is a property of the fluid, right? So it is the property of the fluid by which basically it is flowing, right? And that is what causes the layer which is closest to the surface to stick to it, right? And then progressively, as we move away from it, the layers are less. The layers are more freely moving. Let's put it that way. Okay, they're not being pulled back so much. Now, so essentially, so if I would have, for example, any one of these, say, again, I'm going to draw this 2D plate, right? So now we're going to look at this stuff constantly. So this is my plate, right? And I have a, you know, flow, incoming flow, something like that, okay? And say this is my X and this is the y direction. Now the thing is, if I, so obviously, you know, this the effect of the viscosity is the maximum when we are closest to this, and the farther we move away, you know, it decreases. So so you know, you've heard of this. Now the thing is that by definition, right, by definition, what exactly is a boundary layer? So basically it is that layer of fluid, right? It is that. Now on the outside layer, this is V infinity, right? So very far away from here it is V infinity, right? So if you're closest to the plate here, right? Let's put it, okay, let's use a different color. So if you're closest to the plate here, you know, most probably your velocity is going to be, you know, let's put it this way, velocity is going to be nearly 0, okay, this. Now as you move further, say if you're here, you know, maybe if I were to write the velocity in terms of, this is the free stream velocity, right, this is what it would have continued with, the flow, but then it encountered the flat plate. So then this could be, say, you know, 10% of the V infinity. Then as I keep moving, you know, as I keep moving further, so maybe this is say 20%, you know, of that, right? So if I keep moving even further, say U is say, you know, 50% of V infinity, and so on, right? And then you could take several sections along this, and do the same thing. Okay, so this is what exactly is, you know, what you draw in terms of a velocity profile, right? So if I were to draw just this section, okay, let me call this section as A. So if I want to draw a straight line, and then so this is the point. If I were to call this as, say, 1, 2, 3, 4, right? So at the point here, so this is point 1, right? So this is point 2, this is point 3, this is point 4, right? And this here, it is 10% U infinity, if you see, and then you have that, this is 20% U infinity, and this is 50% U infinity. Okay, so you do that at several of these sections, and then you you know, connect these points, and that's when you get, you know, what you typically know as your boundary layer. That's when you get this kind of a plot, right? That's when you get typically this kind of a plot. Now the question, now usually what you know, what you are aware of, is that this velocity is 99% of U infinity. So this is percent. So 99% of U infinity. So that's basically a way of looking at it. Okay. So you're basically saying is that it's almost recovered, right? Going from zero here, right, which is at the plate. So here it is 0. Right. So it has recovered, it has slowly, the velocity increases as we go away from the plate, and it's almost nearly equal to the free stream, and after this, you know, there is no retardation and it is usual free stream, right. So that in conventional sense is essentially the boundary layer, okay, where it is basically the distance, right. It is this distance, you know, by this distance, I'm going to call it just h for now, okay. This distance after which, by which time or by which distance it recovers almost its complete velocity, because the way you look at that is that the free stream comes in, right, the free stream comes in, and if you're close to the plate, it is 0. It comes in with the velocity U infinity, but it becomes 0 here. So you retard it and it becomes 0 here. So it recovers this U infinity at a distance h. It recovers it completely by the time only at a distance h. So, this is in the conventional sense is basically your boundary layer. Okay. And therefore, it would be fair to say that if I were to draw here, and so if this is my boundary layer, so yeah, I could say that the effect of viscosity, so effect of viscosity is not 0 here, and here it is, because outside of the boundary layer basically here is nothing but free stream. So, at every you can see therefore that at when x is small, closer to this edge, which is the leading edge okay, of the plate. So, at this x, okay, it takes a smaller height to recover the entire free stream velocity. Isn't it, even by the look of this, when you have a boundary layer like that? So, at a smaller distance x from this leading edge, we can say this is x is 0 here, at this say x 1, right. So, you need this h. So, okay, let us erase this bit. Okay. Or let me draw another one. Okay. I am going to draw another one. So, here you have your plate. Somewhere, and here x is 0, right, x is 0, and let us say, so you and say this is your boundary layer, okay, this is your boundary layer. Okay, I am considering this bit as x is 0. Okay. So, if I do that, so then if you see, I am going to take two sections, one section here and one section here. So, by definition we say the height which is required to recover the entire free stream velocity. So, this is what it came in with, okay, which is say u infinity. So, at say x location, say this is x 1 and this is x 2, okay, it needs h 1. And this needs h 2, right. So, what you basically see is that h 1 is the distance and the velocity here is 99% of u infinity. So, if I were to do a close up, if I were to do a close up of this point, of this little point here, right. So, and I come here. So, then what you basically see is that this is your boundary layer. Okay. So, then say at this point, which is say just inside, I forget this. Okay. So, just inside, okay, just inside of this is 99% of u infinity, and just outside of that is u infinity. Okay. So, this is your 0.99 u infinity. So, that is how we kind of look at that. So, that is what this means. So, at x 1, so essentially at x 1 we need a height h 1, so that I recover the entire free stream velocity, and at a height h 2, when at a further distance, I need a height h 2 to recover, because again here the velocity is 99% of u infinity. So, therefore, if you are further down, right, along x direction, you need a larger height, okay, to recover the free stream velocity. So, therefore, now the question arises, okay, that how will the velocity profile therefore look like? Okay, in the sense, I want you to think about this. We will answer this question later on. Okay, I want you to think about this, that if I have okay, let us use this. If I have this, okay, so how does this look like? Okay. How does the velocity profile look like? What do I mean by that? In the sense that if I take say h 1, if I take h 1, right, it is the same h1 height, and I could take any distance less than h1 as well. I want to know whether this velocity vector, okay, the velocity, say, vector here, right, at h1 at location x is larger or less than the velocity at the same height h1, but at x2. Okay. Similarly, if I were to take another, another vector here, right. So, how do these compare? So, if I were to compare, say, this vector, so velocity vector, I am going to call this v1, okay, x1. This is also v1, but x2. This is v2 x1, this is v2 x2. Now, the question is v2 x2 larger than v2 x1 or less or equal, and what about v1 x2 and v1 x1? That is the question. So, that is what we kind of we'll try to answer that in a bit. Okay. So, that is a little bit about what boundary layers are all about. So, essentially, just outside the boundary layer, since it has recovered, so basically it is potential flow, because here you have recovered, in this zone you have recovered the free stream, and the effect of viscosity is not dominant. Now, this is something that Prandtl came up with, and it was he kind of almost like intuition that if the viscosity effects are closest to the body, then why don't we sort of do that? We kind of segregate that area, find out equations which pertain particularly to the boundary layer, and we will solve those along with other equations which are valid for this zone. So, that was his idea, and that is when we come upon Prandtl's boundary layer theory. Okay. Now, before we so we've kind of talked about this, let me pose a problem. Okay, let me pose a problem so that we kind of somehow get an idea as to what exactly we will be doing in terms of trying to study this. So, okay, so let the problem looks like this. Okay, a long thin flat plate, okay, is placed parallel, okay, forgive my artwork, okay, to a 6 meters per second free stream, okay, of water at 20 degree centigrade, 20 degree centigrade. Okay. The question is, at what distance x, right, from the leading edge right. Leading edge is basically the edge which meets the flow first. Okay. Edge will the boundary layer thickness be 1 inch. Okay. And given at 20 degrees centigrade, kinematic viscosity of water is 1.01 10 to the power minus 6 meter square per second. Okay. You get the problem. So, basically we have a flat plate. Okay. So, it encounters, okay, 6 meters per second free stream. Okay. And so, at what distance? So, this is the leading edge. Okay. This is the leading edge and this is the trailing edge. Okay. So, at what distance x from the leading edge? So, therefore, now this is going to have a boundary layer, right. Say it is going to have a boundary layer. So, now the question is, at what distance will the height of the boundary layer be 1 inch? What is this distance? Right, this is equal to what? This is the question, and the height of the boundary layer is given as 1 inch, okay, which means that at this distance x, 1 inch away from the plate, the velocity is 99% of v infinity, which in this case is, see that it is almost recovered it, it is almost 6 meters per second. Okay. So, this is the question. So, what exactly is this distance? This is what we are talking about, and what is given to you is the coefficient, the kinematic viscosity coefficient. Okay. Now, in order to do this, okay, let us go ahead and yeah. So, let us, what we will try to do is do some math. Okay. Let us try to do some math, and then we will come back and try to solve this problem, or try to, in fact, you will be able to solve this yourself, okay? And now that you understand this. So, basically I think that the way the problem is here, what we are trying to pose, right, is that what we are trying to pose here is that what you need exactly here is a relationship, okay, of this height of that boundary layer with the displacement, isn't it? I think that is what we need here. So, we will try to find that out. Okay. So, let us do that in the next module. So, we will try to find out that, and also there's this word called what is the thickness, right. So, there are these terminologies which are associated with the boundary layer thickness, right, displacement thickness, momentum thickness, so on and so forth. So, we will just start understanding those things, like right in the next module. Okay. So, that is for now.